Right, good morning. You may remember that we were discussing the fantastic structure that is the ear as part of our initial exploration of the wave senses. We're only going to do audition and vision as wave senses. The ear provides a wonderful, kind of very accessible example of how we go from physical dimensions to psychological dimensions. Although we've already kind of simplified things a little bit, and that will come up a little bit later as I'll get you all the way down to, wow, this just seems like such a nice, neat story, and then it turns out that this would be a perfect story if we lived in a world where everything was sine waves. Alas, we don't. Or maybe that's a good thing that we don't, because that would be really boring. Back to the ear itself, we had divided it into three different kind of functional areas, as they have done traditionally. So we have this collection area here. We have this, what we're calling a transmission area here, where we are here, we're gathering acoustical energy, which is really vibrating sound molecules. That's the compression waves that are going through the air. They're literally compressing the sound molecules, which then expand, they compress and expand, and that's the transmission of the wave. Okay, so that's what's being collected at in this part of the structure. And then that set of waves is impacting here on the tympanic membrane, which transmits force through these little bones. There are three little bones connected there, which we'll talk about in a moment. The little bone kind of form like a little lever system, and they are moving at the same frequency as the original sound. A little membrane here impinges on a circular spiral, I guess would be better, canal filled with fluid. Right, so it's literally vibrating with fluid. Right, so we've gone from vibrations in the air through vibrations on a membrane, which then cause vibrations in the bone. Although those are nice, those are sort of nice mechanical vibrations like you would have on a little lever system. And then what we end up with is vibrations in fluid that are set off through this canal. Okay, crazy. How does biology come up with these things? But that's where we are. And then from there, we're going to have an auditory nerve going out, because this last step where we vibrate the fluid, turns out there's one last little detail, which is that the vibrating fluid changes the action potentials in a set of neurons, which are, as you'll see in a second, connected to hair cells. No, you heard that right. Hair cells inside the cochlea. Right? Again, how does biology do such crazy things? But that's going to be our story. Okay? And it's a pretty good story. So the transduction part, right, is that part of the story where we go from the physical wave, now in actual fluid, to nerve impulses. That's what we're talking about as transduction. Okay, three separate parts of the story, and that's really where a lot of the focus has been in the research, right? But the other stuff they figured out pretty early, because it's an application of relatively simple physics. Okay, so that's our three-part tale here. Says, dude, you didn't juice me enough. Just not happy. Okay. So the collection part of the story is done almost entirely by what we'll call the outer ear, which is made up of the pinna and the auditory canal. The middle ear part of the story right, where we're having transmission is for us, and this is where it gets a little more complicated. It's going to be the eardrum, the ossicles, and the eustachian tubes, which we'll talk about a little bit. And then on the what am I calling this again? Transduction, right? Transduction, yes, thank you. Transduction side, too many transes. The transduction side, we have the oval window. The cochlea will also have a round window, just to try to confuse you. There's both oval and round in this story. And I'm not trying to confuse you, but that's what they go with the terminology. And then I'll mention the semicircular canals. I'll just mention them here, because I don't think I actually do mention them later. So the semicircular canals, you don't have anything to do with hearing. They have to do with your vestibular system. Okay. And we're not really doing the vestibular system right now. Oddly, in biology and its weirdness, but part of the system for keeping your balance in, spatially at least, with the system for doing audition. So the semicircular canals are another set of canals filled with fluid that the fluid moves as you move your head. And that motion of that fluid was also detected by hair cells, and that helps you with your balance. So that's all you now need to know about the semicircular canals. Okay, so let's talk about the pinna and the auditory canal. So the pinna is a bit of a amazing bit of acoustical engineering. It channels the sound and in that sort of way amplifies it. Now, of course, you might say, hold on now, to amplify something, I need to inject some energy. And it's pretty clear that your pinna is not like, doing stuff to the sound, right? It's not reaching out and like squeezing down at just the right moment so that it amplifies the thing on the beat or something. It would be great if you could do that. That'd be a YouTube video worth having, but that's not what it's doing. Its shape is selecting and actually causes sounds in a particular frequency range to be of greater amplitude than they would be without the, which is a feat of acoustical engineering that's pretty cool. It also, I'm going to have it up here, but it also does a little bit of filtering. So it sort of focuses your auditory system within a particular range to some extent. Okay, so it acts kind of like, I'm not going to go through the different types of filters. It acts sort of like a filter. Okay, think about it that way, and it sort of emphasizes a particular range in the frequency. Okay, so that's pretty amazing, given that it's just this funny looking sort of thing. The auditory canal, well, as far as I know, just kind of a place for the sound to go down. Maybe it has some properties we haven't discovered. Tends to fill with wax. Yes, that's something. But that's nothing particularly exciting. So that's the collection part of the story and our outer ear discussion. Okay, so short. So on to things a little bit more interesting, and you'll see that while I'm doing the different sections, there's also kind of a temporal, bless you, sort of a story about here comes the sound. First it's in the outer ear, now we're going to the inner ear here, right? So this, go here, this is the tympanic membrane, okay? And the acoustic energy as it comes in here vibrates the tympanic membrane, which in turn causes vibration of these three bones: the malleus or hammer, the incus or anvil, and the stapes or stirrup. Okay, so mixing metaphors, I guess those are all, I don't know, all things found in a blacksmith shop or something. I don't know, maybe. But the stapes is where the action is in terms of intersecting with the oval with myself. Oval, thank you, oval window. Okay. So the stapes is connected, well, to the oval window and is literally moving. Okay, so it's this little prongy looking thing here. Okay, and it is vibrating at the same frequency as the tympanic membrane. And there's kind of a sense in which the air vibrations have to be made stronger so that they become capable of moving the fluid, right? So air resistance, not so much. Fluid resistance, considerably greater. So that's part of what's happening here, is that this lever system is actually creating the correct level of vibration at that window. Okay? So in the fluid, it vibrates at the right frequency. Yes, go ahead. Did I say it wrong?
It's not on any of the slides, so I was just curious.
Oh, I'm sorry. Yeah, so the round window is at the same level as the oval window. Yep. Yeah, so let me explain the round window. Well, since you brought it up. Yes, so it's part of the inner ear. The round window is this dude right here. Okay. It is, so the reason the round window is there, you can say such things about the purpose of anything, is that the fluid inside the cochlea, right, takes up all the space. Right, it's completely filled. And this fluid, not all fluids, but this fluid is completely non-compressible. So if you didn't have something that could vibrate in opposition to, that's not the right word, what's the right word? What word am I looking for? When the tympanic membrane goes in, the little membrane on the round window has to go out. Right? They got to go contrary to each other. Otherwise, you would just go like up against the fluid, you just go, oh, okay, that didn't work. Right? So that's what it does. So that's if it gets frozen up, you can't hear no more. Right? Even though it doesn't seem to have much function other than that. Does that help? Okay, so we now have vibration of the ossicles, and then at the oval window. Oh, now it's good. Okay, so now we've arrived at the more interesting parts of the story. All right, we've gone through transmission, and now we're getting into the transduction part of the story. So this thing here, you may recognize from the previous slide, is kind of like a blow up of the cochlea, sorry. It has all these cochlear names. So there's cochlear fluid, there's a cochlear duct, and so on. Let me jump back just so you see where we are. So we're taking this guy here, the cochlea. We're now going to extract it, put it on the next slide. I'll reorient it so that we can see it a little bit better. Okay. So here is the stapes, right? Sort of the end of our transmission story, and now the beginning of our transduction story. Is doing its thing, vibrating at the oval window, causing the fluid inside the cochlea to vibrate. Okay, so the cochlea is a complex place. It has sort of these two canals that they get named, but don't worry about it. Two canals here and here that kind of connect at the very, very tip. And the tip, so to speak, is the end of the spiral in here. Okay, so there's a little space where they can, where the fluid can flow. So this is that round window we talked about before. Here's the auditory nerve, and here is this area. This whole area here is Most people call this the organ of Corti. There are two membranes that will be concerned with, the basilar and the tectorial membrane. And the important thing to know is that they are resident in between these two canals. Okay, so there are these two separate canals. In between them is what we can call, just generally, we can call it the basilar membrane. It also has the tectorial membrane in there too. Okay, so that's the picture. We have the vibrations happening here, and they just go down for our purposes. They go kind of down the cochlea. Now, of course, down the cochlea is actually round and around the cochlea, but that's just a space-saving thing, apparently. There's not, the spiral itself, to the best of my knowledge, has not played into anybody's figuring of how this works functionally. Okay, yeah.
So the organ of Corti is composed of the tectorial and basilar membrane. Would that be a right statement?
Sure, let's say that's true.
Okay,
Yes.
And then
That whole area is really the organ. I realize this slide does not suggest that that's the case, but yes.
okay, and then I see how the vestibular canal is filled with fluid. Is that the same for the tympanic canal? Or?
Yes, indeed, and in fact, let me see if on the next slide things become more clear. They don't, not there. They don't there. There. Let's try that. So this is obviously a little bit more schematic, but this is the lower one is called the tympanic. This is vestibular, but you see they're connected up in here. Okay, so think about it as two canals, one on top, one on the bottom. That's all you need to know, and they both have the same cochlear fluid in there. Okay, and the waves travel down those canals. Okay. And I'm not doing too much harm to the story by saying it. Make sense? Other questions? Yeah, it's a funny, detailed place, and we're kind of, we have to make some decisions about how much detail. So if you take a course in sensation and perception, you'll get more of the story. So it's a very involved story, but you get more of the story, and it's actually a really interesting story. Okay. So we were there. We were there. Yes. Okay. So far, so good. Other questions? So it's important to stay oriented because it is a weird system. So if you get lost, you're really lost. Other questions? Want to locate something? Okay. Okay, so these waves now are being kind of generated here, right? And now are essentially flowing forward, just like if you had imagine a pan of water and you vibrated at one end, right? You hit it at one end and the wave goes down the pan. Right? And it sort of eventually will cause the round window to expand and then contract back. Right? And then the next wave comes. And of course, that all happens very, very quickly. Okay, so far so good? So the waves, the frequency of the waves, and the vibration of the basilar membrane, which is essentially being vibrated by the wave, okay, is essentially flapping in the wave, if you will, right? Is riding in the wave, just like a flag would, or like a filament would, if it were in a fluid that had waves in it. Okay, just that kind. That's the right physics. Is moving at the same frequency. Okay, so when you have 100 hertz outside in the air, you get 100 hertz on the basilar membrane. Okay, which is pretty amazing feat. Imagine that's your engineering project for acoustical engineering. Make something that vibrates in fluid at the same hertz that it vibrates in the air. You're like, where's the drop slip for this course? That's really hard. Okay, everybody all right? Okay, so now the story gets even stranger. The hair cells on the basilar membrane, right here in the organ of Corti, are literally moving. There are some which are embedded into the sectorial membrane. And there are others that are just there, like, you know, floating around in the cochlear fluid. Distinctions we don't need to go into, but there are those two different types. When there's a wave, either the movement, the added movement from the wave, or literally the shear, right? It's like when you have your, you know, the hair on your arm or on your neck, something gets caught in something and you have that little pulling. It's just like that. Except it doesn't hurt, it causes you to hear. Okay, so the ones that are embedded into the sectorial membrane from the basilar membrane are like literally like between the two membranes, and you get this little, right? And that causes a pulling of the hairs. The cells depolarize and they send a signal down the auditory nerve. To make a somewhat longer story short. Okay, questions? Right, and you can see that kind of sort of, and I'll show you maybe a little bit better picture in a second, sort of kind of here. Right, these guys are the hair cells. Right, and you can see that that whole structure is kind of resonant in between the two canals. And we're calling that whole thing for right now the organ of Corti, which is kind of riding on the basilar membrane. Pretty close to good. Good enough. Okay. Right, and so then this, you know, then the auditory nerve, and then we go into the brain and hope the brain can figure out what the hell's going on, because so far all we got is a bunch of neurons firing. But that's a story for a few minutes from now at least. So these are electron microscopy image of hair cells. That's what they look like, at least measured in this particular way. There are about 16,000 hair cells in each ear. They are of varying stiffness, and that stiffness is part of what gives them sensitivity to different frequencies. The basilar membrane itself is also of varying stiffness, and that too gives its sensitivity to different frequencies. Right, so it's stiffest, closest to the stapes, and it's most flexible towards the apex. So here we have a too detailed figure, but sometimes it's nice to at least get a picture, and then don't worry about the things that we haven't talked about. You can see there are going to be some membranes and such that we haven't talked about. But we're really kind of focusing in here on this organ of Corti area. So here, this is the inner hair cells are the ones that aren't connected to the tectorial membrane. Don't worry about that. The outer ones are connected to the tectorial membrane. Whoops, that's a typo. And right, so here's basilar membrane, tectorial membrane, and then here you can see, you know, the artist has tried to have some of these axons here, leading to some ganglion cells, which do some of the initial auditory processing, so to speak, and on we go to the brain. And so when we have acoustic stimuli, we sometimes, this is one way the transmission can work. Essentially, we have a breaking of or pulling, I should say, of linkages here, sometimes breaking, I suppose, which causes depolarization. So that's a kind of a blow up of what's happening. And all that inside the cochlea, inside this two kind of membrane sandwich, so to speak. All right, so that's anatomical still. So what does it all do? How does this all work in terms of the perceptual side and making you be able to hear all these different frequencies and loudnesses and actually like really complex noises as well. So I'll tell you about part of that, and then I'll throw up my hands for the last part. So, as I mentioned, the basilar membrane is differentially sensitive to sound waves of different frequency. So the maximum energy, its kind of resonant frequency, if you will, is different as we travel from the base, which is here by the oval window where the stapes is, right, to the apex. So the wave is traveling in this direction, right, and this is the basilar membrane, and this is supposed to show you some wave traveling down. Okay, so that's all very fine. This is that same dimension here, okay, so distance from the stapes or the oval window along the basilar membrane in millimeters. And then this is the relative size of that traveling wave and where it peaks out, right? So at about 16 hertz, it has a peak at around 20 millimeters. I say 1600 hertz. At about 20 millimeters along the basilar membrane. Here's 400, here's 100. Okay. So this led people to get very excited, saying, look, where the maximum energy is for waves of different frequency is how the system is deciding what the frequency of the sound is. Right? It's like a coding system, their words, like a coding system for what the frequency is, right? So if I have the most stimulation in this region, right, way down here, then I must be at 100 hertz, let's say. Well, if it's over here, well, that's more like 400 hertz, and so on and so forth. See what I mean? So it's obviously it's just super schematic, but that's the idea, is that where that maximum energy is residing, right? That's where the neurons are. That part of the basilar membrane is going, whoa, I'm really into this. This is a really good sound. And out goes your signal that, yeah, that's a sound at this frequency. Right? Now, obviously, it's got to be a lot more complex than that, right? But that's the basics. So that was thrilling for them, right? They seemed to have a story that worked. And so here is more of a map of that. Okay, and so this is kind of summarizing the location where the maximum energy is for waves of different frequencies along the basilar membrane in this very schematic kind of way. Okay, so here again is where the stimulation starts, right? This is the oval window or where the stapes is, right? And now this is showing you without giving you any like numerical details of how far down, but you get the idea. So if you're really high frequency, like 20,000 hertz, that's really high frequency, right? These guys get excited, but down here, no, that's all. Right, 7,000 hertz here, 5,000, right? Speech would be way out in here someplace. And even like a flute is like over the highest note it can hit is up here, right? So all this stuff, kind of interesting that it's there, right? Because it's like really hear things that I hear too often. But anyway, that's we're here. So that's that. And then these are individual examples, right? So this is low frequency, right? Again, would be out here. This is kind of this unrolled. Hopefully that makes was immediately apparent. Medium frequencies are kind of in here, and then again, high frequencies. That make sense? Questions? Yes.
What calls this the place theory? Would that be
I
right?
am just about to get to the place.
Okay.
Yes, yes, it is. Yep. Yeah, so I kind of back into place theory and then back even further into frequency theory. So yeah, so there are two competing theories. This one is called place theory. Before I get into place theory, I should say that the size of the wave, right? So we've just been talking frequency, but if you remember, there's frequency when we do the physics of sound, can be the easy physics of sound, but there's amplitude too. So frequency is how many cycles per unit time, usually seconds, so we get to hertz. Amplitude is how big the wave is. So we can pull those two things apart. Those are the easy dimensions to pull apart. So the size of the wave, right, depends on in the whole system here, right? Depends on the amplitude of the sound. The frequency of the wave is another story. Okay? So the bigger the wave, the more activity in general, and then the louder the sound is perceived. So the sound amplitude as a physical measurement, sort of, right? It seems a little circular almost, right? So the sound amplitude, remember that's just a physical event. And then there's your perception of loudness, which of course, if all is going well, scales nicely with the actual physical amplitude. But the magnitude of the wave is what is making that happen in the auditory system. So the greater the amplitude of the wave, the more activity there is in the neuronal system. That part of the story seems fairly straightforward. This brings us to a contrast between what was trotted out as place theory when they discovered the dependency between sound frequency and location in the basilar, along the basilar membrane. And I'll roll the other one out just because we'll have a thing to contrast. What they call frequency theory, which also seemed to play a role, and there were lots of results that were consistent with frequency theory. So place theory is pretty much explained right here. Right, so where you are, where the maximum energy is, I should say, in the basilar membrane, is a way to code up what the frequency of the sound. Right, so that's that road we just went down. The other theory, frequency theory, we kind of alluded to before. The frequency of the wave vibrations, right, is the same as the frequency of the sound, and the neurons are going off at that same frequency. Right, so a wave goes through, it has a particular frequency, and the neurons are going off at that frequency too, which has a little complication in some ways because it's like a refractory period for neurons and stuff, but they can overcome that. It turns out that sort of the received wisdom now is that both of these have their place, maybe. I may not say place, both of these have an element of truth to them. So sure that's really the case. But anyway, that's what I'm supposed to tell you, and that's the received wisdom right now. So the place theory seems to work best and most definitively for moderate to high frequencies. So moderate to high frequencies. So high frequencies, right? Well, these are nice. This is a nice way to do it. Moderate, so these guys and up. The frequency theory, right, which is this time lock theory, essentially, saying that there's a time locking between the waves and the neuronal firing, seems to work best at low frequencies. Okay, so stuff that would be way out here. And that's kind of kind of where they have settled. Of course, people are still working on this, and it's one of the areas in psychology which is like super practical because deafness, either congenital deafness or deafness, that's super common due to aging, seems like it should be kind of addressable here, right? And so, hearing aids, for example, are very much into these theories. Like, well, how do we boost the energy going into the ear to help hearing? We need a theory of hearing in order to do that. So that's why it's not just good enough to like put an amplifier into your head, although that will work to some degree, but not the best way to do to aid hearing. Okay, so let me stop there. Questions on all of that? I realize that was kind of a lot. No, really? Yes.
Are the placement opposing theories? Do they work together?
They were originally opposing. So the question is, were the place and frequency theories opposing theories? They were like super opposing theories initially. Like, like these people really don't have it. But I think now they sort of jointly explain the data. So yeah. Other questions? Yes.
Hair cells like side.
So the hair cell, let's go back. So they're not really inside the basilar membrane itself. They're in this area that's kind of between the basilar membrane and the tinctorial membrane. There should be an O in there. And it's like they're growing out of the basilar membrane up, and some of them then get connected to the tinctorial. It's a little hard to picture. Imagine finding this thing for the first time, like you, right? We get it. We probably not. We didn't do the investigation on with a cat or right. You're like, what's this? What's with these hairs? It's very confusing. Other questions?
We don't need to know the difference between inner and outer hair cells.
Yeah. So there's a whole other. So if you take some perception, I'm not trying to sell it, but if you do, turns out the hair cells are like more actively involved in this. It's very interesting and well understood now. So like they create. I think about it this way: they do kind of some of the early processing of the sound. Okay. Okay. Shall I go on? Okay. Let's go. So we are here, right? This little guy. Wow, that whole trip, and all we did is explore the interior of that tiny little thing. So out comes the auditory nerve, which then goes to which then goes to the auditory nerve, which then goes to the medulla. There's a cochlear nucleus in the medulla, and then eventually things get passed on to the thalamus, and eventually into the temporal lobe, where we have more and more auditory processing type things happening. There's obviously an extensive body of work about what happens after it leaves the auditory nerve, right? It seems like, wow, that's a lot to understand what's happening at the auditory nerve level. It turns out that's like just the tip of what needs to be understood in order to get to perception. So that's tricky. Usually we think about the temporal lobe as sort of finishing up the processing. The processing tends to be disproportionately focused on things in the middle of the spectrum. So it doesn't sort of equally do the entire range of, the auditory spectrum that, you know, where you can get some detection. And of course, out of this, we're going to get things like speech perception, music, I guess, perception and appreciation, but also other things that are easier to handle. We won't do speech perception, but things like sound localization. So sound localization is one of those kind of underappreciated abilities because, again, you're so good at it, and it just seems like it's like the information is self-evidently given. Right? You're just like, well, of course it is. I heard it there because it happened there. But you have to remember that your ears are here, right? And the sound is here, even when the event is there. You know what I mean? So it's not like the sound doesn't come with like directional vector attached to it. It says, hey, by the way, northeast and at this elevation, right? But somehow your system goes exactly like, hey, it was over there, right? Even though, again, the sound is impinging only here. So that's pretty good. So that's the kind of the big mystery of sound localization is how can you have acoustic energy always be, at least on your body-centric scaling, right? Your body-centric frame always comes to the same place, right? And yet the perception of the sound event changes pretty reliably with the sound event. Right? So that people in psychology being, you know, liking that kind of mystery said, hold on, now that's a problem. Let's see what we can do to solve it. There's some pretty good attempts to solve it. So one way to think about this is to just pretend you only have one ear. Right? That'll simplify things. Because you can do sound localization with just one ear. You're not as good with just one ear, but you can do some. So that suggests that there are monaural or single ear cues. One of those cues is the distortion that you get from the pinna. That distortion changes depending on where the sound is coming from. So it's as if your pinna puts a little spin on the sound when things are coming from behind you versus in front of you, side. It just slightly changes it. And your part of your system is capable of detecting that. And you perceive it as patient. So that distortion. One ear can do some sound localization, but two ears are indeed better. So because the ears are at physically different locations, we have a number of information sources that are kind of trading on that difference. The first one is very simple. Under some conditions, or maybe I should say at some locations from you, some spatial orientations from you might be better, there are sound level differences or loudness differences at the ears. So if somebody's right in front of you or directly behind you, those differences disappear, right? Because it's equally distant. Somebody's directly like on your midline, right? Whether they're in front of you or behind you. So this works when someone's off midline, because if, to the degree that someone's on my right side, any sound they make reaches this ear with a more intensity, more loudness than this ear. Okay. And that's just because of the way the ears are facing, and because my great big fat head is in the way. So the closer ear gets higher intensity. There's also a timing difference that the system is sensitive to. So there's a very, it's only the speed of sound, it's not the speed of light. So there's this very, very little timing difference that, again, is because something over here is closer to this here, it gets there just a little fraction faster than it gets here. Right, and so you can imagine how they discovered this. I mean, it's pretty obvious. You bring somebody into a lab, you keep the loudness exactly the same, you change the timing just slightly, and people will report hearing the sounds at different times. Right, and of course, that is what is done in stereo. They still do this. This was such a big deal in stereo. Right, they made motion across the speakers. It sounded like, you know, a truck was going by, like changing the timing sound or changing the intensity of sound very clearly, because they were just doing engineering. So the timing difference is such that, of course, the sound always arrives earlier at the closer here. Right, so here's William James, right? So we have sound arriving at one of his ears, right? And the closer ear gets the sound first. And again, that timing difference is the sort of the key to that cue. So that difference is super duper small though. So amazing that you're sensing something to it, it's so small. So 0.63 milliseconds. All right, so the last part of this, we will just, we'll talk about human hearing versus animal hearing. People are interested in other species, of course, just intrinsically, but also kind of to place humans in the bigger mix. So human hearing, so this is a log scale in terms of hertz, which are cycles per second. So these are low frequency sounds. These are high frequency sounds. Speech would be kind of right in here for us. And just to locate you, all right? So this is our range, and this kind of vanilla coloring is to kind of give you a sense of that range versus each one of these other creatures. So an elephant has much lower frequency sensitivities. Not quite as high, but pretty close. So generally a wider range than we have. Dogs don't go down quite as far in terms of their sensitivities, but do hear at a higher frequency level than we do. So the famous, you know, the dog whistle you can't hear is above our range, but still within theirs. So cats, pretty similar to dogs, but you never know with a cat if they don't hear what you're saying. Not like dogs. Dogs come every time. Cats don't hear whatever yourself. Mice, look at them. Woo. Very high frequency hearing. Not so much down here. Okay. Sorry, I'm on the bat, but the bat and the mouse are very close. All right, so the bat is even higher, right? And famously, some of them do navigation with hearing, so maybe that's not too surprising. Whales, beluga whales, I guess in particular, also have very high frequency. I thought the beluga whales would be like down here in the low frequency, right? To have like that long distance communication. I thought that was going to be a low frequency. But apparently not for them. Dolphins have this tremendous range, almost going as low as we do, but then going way, way, way up high. Right, so is our hearing good? Pretty good. It kind of depends on what what you're measuring and using as your criteria for goodness. It's certainly not covering the entire range that other creatures can hear, but we do pretty well within our range, and we're similar to other land mammals. All right, I will let you go there.